Welcome to this lecture on reactivity and classes of organometallic compounds. This is in continuation with our earlier lecture where we have looked at various type of organometallic compounds, the classes in which they belong to, which are mainly class 1, class 2 and class 3 depending upon the famous 18 valence electron rule. Class 1 types are the ones which does not obey 18 valence electron rules. Class 2 types are the ones which does not exceed 18 valence electron rules, and class 3 are the ones which always obey the 18 valence electron rules. What we had seen in the earlier lecture that there are specific requirements for belonging to each of the classes. For example, for class 1 mainly 3D transition metals fall in this category. Organometallic compounds of 3D transition metal belong to class 1 type complexes. As for the class 2 types, they primarily are of 4D and 5D transition metals and their complexes. And lastly, for the class 3 types, ligand becomes important, and the pi-acidic nature of the ligand is crucial for complexes to exhibit class 3 type of properties. And today we are going to look into this 18 valence electron rule from a critical standpoint, particularly from the complexes which shows deviations from these. For example, for late transition metal compounds, particularly D8 and D10 ones, 14 or 16 valence electron or 16 valence electron compounds favored. For example, for nickel tetracyanide, two minus, it is in D8 system and has 16 valence electron. For example, rhodium dicarbonyl chloride, dichloride minus, is also a D8 system having 16 valence electron. Au Cl4 minus similarly is a D8 16 valence electron. So, what is emerging is configurations like D8 prefers to have 16 valence electron over the conventional 18 valence electron for other complexes. Let us take a look at these 10 systems. For example, AuCN whole 2 minus is a D10 system having 14 valence electrons. This is way too different, significantly different from the 18 valence electron which conventional system show. Similarly, with R3p Au Cl, that also is a D10 system having 14 valence electrons. These systems exhibit a coordination number of 2 and are linear in geometry. On the other hand, for early transition metals, having D8 configuration, 18 valence electron is observed. Examples is FeCO5, MnCO5 minus. So, this discussion is emerging into something very interesting. If I have a transition metal having D8 configuration, then if it is a late transition metal, then 16 valence electron is there in its valence shell. It does not obey 18 valence electron rule. It exhibits square planar geometry and has a coordination number four. On the other hand, if this transition metal happens to be an early transition metal, then 18 valence electron rule is valid. Coordination number is 5 for the examples covered. Let us look this in an example with respect to their placement in periodic table. So, compounds like FeCO5, MnCO5 minus, for them 18V rule holds, whereas compounds like NiCN4 2 minus minus 16 VE rule holes, and compounds like AuCN2 minus R3P AuCl 14 valence electron rule holes. So, what is emerging is that these part belongs to early transition metal and the other part is late transition metal. So, thing that is emerging is 18 valence electron rule is more valid or more appropriate in this region, and deviation from 18 valence electron rule is more in the regime of late transition metal compounds. That is a very important observation, and a qualitative interpretation for this deviation from 18 valence electron rule is provided from the following. First is electroneutrality principle. So, this was first proposed by Pauling, and it says in a sense that if atom metal in our case receives too much electron density by binding to ligand, should also find a way to give back the electron density onto the ligand, and hence the electroneutrality of the atom is maintained, and the factors which lead to metal donating back the excess electron density on to the ligand, it is bound to gives rise to the important concept of ligand p-acceptor ability. This ligand p-acceptor property follows from the electroneutrality principle discussed above and would help in explaining deviations from the 18 valence electron rule. Another important factor which comes into play are the separation of between the n minus 1 d ns and np orbitals. Now, as one moves across a period towards the late transition metal, the d electrons becomes more core like, more like core electrons due to increased effective nuclear charge. With increase in atomic number. The other important aspect is the gap between these orbital increases. Let me illustrate this with the following graph. For example, here we have the energy, the bottom part or the shaded region shows the energy corresponding to the core electrons, and the top part indicates energy of the valence electrons. As we move from calcium all the way to the zinc, all the orbitals 3d, 4s, 4p, they become stabilized further owing to the increase in effective nuclear charge. What is more important though is the relative stability of these orbitals as we move across the period. For example, let us take a look at the d orbital, which moves from here all the way to there, and in the region of calcium and scandium, d 3d is above 4s, whereas in the region of copper and zinc, which is a late transition metal, 3d is now lower in energy than 4s and 4p. Similarly, let us look at 4s orbitals. In the early transition metal region domain, four s is lower than 3d, and in the late transition metal domain 4s has become higher than 3d, and the 4s decreases as such. Now, as for the 4p, there has been a decrease shown by this line, but what is striking though is that for early transition metal, the relative difference between the orbitals is much smaller than for the late transition metals, where the difference has become bigger. As a result, orbital participation of all of these orbital for late transition metal becomes more difficult, and I must note that for 18 valence electron rule to hold, participation of all s, p and d orbitals are required, because there is one s, 3p, 5d having 9 orbitals, leading to 18 electrons. So, that is more possible in the early transition metal domain, whereas in the late transition metal domain, because of these large energy gap, such participation of orbitals becomes difficult and d orbitals become more core like and inert in nature relative to the S and P, and hence it accounts for lower valence electron coordination complexes. For example, for iron system like FeCO5 and FeCnR5, the application of electroneutrality principle becomes prominent. These both complexes are Fe0 D8 system and have 18 valence electron count. These being a late transition metal, the energies of d, s and p orbitals are close, and as a result of metal center being electron rich, owing to coordination to all of these ligands, the metal with the availability of all these orbitals close in energy is capable enough to perform effective iron to carbonyl pi back bonding from the 3D orbitals of the metal. So, the electroneutrality principle is upheld. So, there is a synergism in which the metal which accepts electron from the ligand is able to maintain its electroneutrality by a mechanism whereby it donates back some of the electron density to its ligand by virtue of the ligand's pi acidic nature. For example, for another complex, let us say nickel tetracarbonyl, here too nickel is in 0 oxidation state having D10 configuration exhibiting 18 valence electron with coordination number 4. What happens when and nickel is bound to a pi acidic CO ligand. Nickel is bound to a pi acidic CO ligand, and whereby nickel can give back electron density onto the ligand. On the other hand, in the complex which is nickel tetraphosphine, here also nickel is a 0 oxygen state having D10 configuration, but PR3 is a relatively weak pi acidic ligand. As a consequence, because of the lack of the back bonding, this complex sort of stays in equilibrium, favoring a different complex whereby NR PR3 and losing a PR3 ligand. Here too nickel is in 0 and D10 system, but 16 valence electron count having coordination number 3. So, what we saw in this lecture is that the late transition metals show deviations or has a tendency to show deviation from the so called 18 valence electron rule, and these late transition metal particularly of D8 and D10 configuration are more common in showing this deviation from 18 valence electron rule. The deviation from this 18 valence electron rule for late transition metal has been explained by electroneutrality, pi acidic nature of the ligand, and also the relative stabilization of n minus 1 d, ns and np orbitals, in which as we go across the periodic table to late transition metal domain, the d electrons become more core like and they sort of resist from engaging in valence bonding. So, with this we have concluded a series of lectures on the properties, classifications of organometallic compounds, and then we are going to take up something more interesting in the next lecture, that will be on the classification of the metal conjugate, or rather the ligand partner and their reactivity. So, I thank you for being with me in this lecture, and I look forward to being with you in the next lecture, which will look at various kinds of ligands available for binding to metals in the organometallic compounds. Thank you.